Okay, so here's where we were last time. We were talking about using the polar coordinates formulas as a change of variables function. So reminder, you can think of these equations that convert from polar coordinates to rectangular coordinates. You can think of them as, in those terms. You can think of it as, well, if I'm in R2 and I've got these coordinates, but I want those coordinates. You can think of it, and they're good for that, and that's fine. But you can also instead think of it as a change of variables function, right? So that's a different perspective on what's algebraically really the same thing. So next thing that you can do is you can compute the stretching factor. And under reasonable conditions, namely the convenient assumption that R is not negative, stretching factor, easy to compute, nice, compact answer. Finally, when you do the pullback, now keep in mind, doing change of variables, the idea is we think of an integral on the domain on the right, the integral on the defined on the target domain is pulled back to an integral on the pre-image domain, or the pullback domain. You can think of it that way too, but again, there's a different way to think about that, which is to realize that everything you need to know from this picture, you can see it on this picture, right? So, for example, if you want to, let's think about theta slices. Well, that's what a theta slice looks like. Yeah, sure, that's what a theta slice looks like in our theta world, right? But that's what that slice looks like in XY world. So we don't really need to draw that picture. You can see everything you need right over here, right? So that was the big idea that we came up with. Just declare that we're going to use this as our change of variables function. That's how we're going to plug in for x's and y's. There's my stretching factor. Look at your bounds in the xy plane, and boom, there you go. All right, so we did an example last time. We talked through the details of this example. I won't go through the details again. But we were able to use these ideas to observe that this integral defined on this domain, which I want to take a moment to recognize, is a pretty undesirable domain. Right, that domain there. It's got one of the edges is a circle. If you slice up that domain, dx, dy, rectangular coordinates, there's square roots in your inner bounds. That means that there's square roots in your outside integral, and that means you have an annoying integral. Probably. Possibly. So if you take a polar coordinates point of view on this, here's the pullback domain, but we don't even really need to think about that. Notice that you can see everything you need here. Theta goes from 0 to pi over 2. There's our theta bounds. I see it right here in this picture. For a given value of theta in that range, R starts at 0 and R ends, it ends on that circle. That circle's on the boundary of the disk. This is the unit disk, and so R equals 1. So my R bounds 0 to 1. Don't forget to plug in your stretching factor, and off we go. Right? There's that interval. Okay. All right. So I guess I did a lot of those details again. Anyway. A couple of things I want to point to, though, that we didn't talk about last time. Of course, don't forget to plug in for what x's and y's are. Now, that's just plugging straight into the change of variables function, or, if you prefer, plugging into the known conversion formulas from polar to rectangular. It's just plugging in, right? Nothing tricky happened there. So don't forget to do that, though. The other thing I want to point out, and a lot of students get confused on this, or I don't know, there's a misunderstanding of sorts. But of course, it is a very big deal that we replace dx dy with r dr d theta. Again, I have encouraged students to think of R, think of this as a single thing. This is, as a group, all of that together, that is dx dy, or dA in the xy plane, if you prefer. But that said, when I say it's a single thing, don't take that too religiously. It's a single thing right up to the point where you write it down, but then, that R is part of the integrand. right? The new differentials are dr d theta, right? So your integrand does in fact become r cubed. Right? So make sure to actually include that. I mean, the whole purpose of remembering that factor of r is that it is a factor in our new integrand. So I think some students take it a little bit too sort of rigidly that this is your differential and then sort of draw a hard line here and don't include it. And ultimately that doesn't really make any sense. But anyway. Okay, so your new integrand like so. Okay, so I'm going to show you all a bunch more examples. It's nice to see various examples on this. So let's start with, suppose your domain is this entire unit disk. Right? What do we do with this? The weird thing about this problem is it's kind of hard to tell where to get started. Where is the first value of theta? Where does theta start? I mean, up here it's kind of easy to see that, okay, well, there's my first value of theta, and then, there's my last value of theta. They're visibly a start and an end. Here, where do you start? Right? This is actually not a bad thing. This is arguably a good thing. There's a flexibility. The confusion comes from the fact that you could start anywhere, right? If you really want to, one thing you could do is you could start at negative pi and think of theta as going all the way around and ending at positive pi. I suppose you could do that. What most people do, just because, I don't know, it seems kind of canonical, the numbers are maybe a little more convenient. It depends on the circumstance, I suppose, but most people start at theta equals 0 and then think of theta as going all the way around and then, of course, ending at 2 pi. So you don't have to, but math, most of the time, people do it like this. And again, we love 0. 0 is a great number. Why not take advantage of an opportunity we have to incorporate 0 into our question? Okay. All right. Okay. Just like with rectangular coordinates, you can slice in either direction. It is fine to do either way. You can do d theta dr if you want. The only thing is, it is almost always better to do the slicing in this order. It's just more common than not that we think of r as being a function of theta. Remember, and the general idea is whichever one you think of as being a function of the other variable, you tend to want to put that variable on the inside. That's one of our strategies for keeping our integration as convenient as possible. So most of the time, this order. In fact, there are not very many examples where you do it the other way, and actually, to your advantage. So it's almost fair to say just always do this. And I think, in fact, it probably is fair to say that, barring someone coming up with a really wacky, obscure, deliberately obscure example, for Math 212, it is always better to do this order. So I'm going to say, for the purposes of this course, always do dr on the inside, d theta on the outside. And I want to encourage y'all, I said this before, let me say it again, I want to encourage you to think of dx dy, our area element, we sometimes call it, our dA, as we recognize it from the section on double integrals. Think of r dr d theta as being a single thing that is that dA. So in other words, don't ever just write down just dr d theta by itself. Why would you do that? Under what circumstances, right? I mean, the whole point of doing an integral in polar coordinates is that we are trying to use that as a tool for computing an integral that was originally in rectangular coordinates. Well, that dx dy is not dr d theta. It is not. They are different, right? What it is, and always is r dr d theta, right? So it just doesn't make any sense to just write down dr d theta by itself. Let me show you the pitfall that you can land on if you are a little bit too careless on this point. You could, for example, on a question like this, you've got this given to you, and you're trying to build up your polar coordinates integral, what you might end up inadvertently doing is say, all right, well, we're going to do an integral dr d theta. And, okay, well, let's think about our bounds. And you start thinking about ranges of values of theta and ranges of values of r and drawing the pictures and the slices and thinking about geometry and stuff. And you get so wrapped up in thinking about that you might just plumb forget to write down your stretching factor. And I've seen it happen a million times. It's a routine, right? Now, of course, I'm making a big deal out of this today, right? Part of why I make a big deal out of this is that I'm hoping to turn this semester anyway. I see this happen a million times to I see this as little as possible. That's my hope, right? I don't want anybody to step on this little landmine and, oh gosh, I forgot my stretching factor. But honestly, my experience shows that even after making a big deal out of it in class, there's still going to be some students who will forget, who will write down dr d theta, because after all, I'm accustomed to writing down differentials first. I'll worry about the integrand later. The big work of the matter is to figure out the bounds, right? And then just clean forget to write down that stretching factor, right? So you can avoid this landmine by just write down dr d theta like it's a single thing all at once. And don't ever write this down by itself when you're doing one of these kind of integrals. Okay. All right. That's just advice. It's just a suggestion. Okay. Okay, more examples. Let's suppose we're doing an integral. Oh, here, let me do this in blue. An integral on this annulus, we call it. This kind of ring. I like to think of it as being kind of a moat, right, around an island, thus the blue, right? So suppose we want to do an integral on that annulus. Now, why would we want to do an integral on this annulus? I mean, look, maybe I want to compute the amount of water in the moat, right? And I know a formula that tells me depth as a function of position. Maybe, whatever. It doesn't. It's not. We're not going to concern ourselves with why we want to compute this double integral. Let's compute this double integral. So notice we have double integral given. We have an integrand given, appropriate to the application, whatever. And how do we compute this? Now, a lot of people will tell you that a good way to compute this integral would be to compute the integral on the entire disk, and then subtract from that the integral on the inner disk, right? Yellow minus purple. Shouldn't that give you an integral on the moat? And, often that's a good strategy. But the problem is you can't do that here. You can't do it because this function is undefined at that point. So an integral on the disk is not defined. And, you might want to say something about, let's improper integral, and maybe. But we haven't defined improper integrals yet, and there are some circumstances where even with the definition of an improper integral, it might turn out that the improper integral is not defined, right? It's simply, you can't do it. So even though those two integrals on disks might not exist, and certainly are not yet defined, there's nothing wrong with asking for this integral. The integrand is perfectly well defined for every point on that domain. And all this business about, just include the origin, bad idea. Right? Okay, so let's talk about how to do this integral. This is a nightmare in rectangular coordinates. After all, when you start slicing in rectangular coordinates, you're going to sideswipe there, and then you're going to have a region up here, and then you're going to have a region sort of down here. And then you're going to have a last region over here. You're going to have 4 separate regions. Yikes, nobody wants to do that. Plus, by the way, square roots everywhere, right? So this is highly undesirable. But look how easy in polar coordinates, right? In polar coordinates, our theta starts at 0, goes all the way around to 2 pi. So the theta bounds are 0 to 2 pi. For a given value of theta, so on a given theta slice, What's the range of values of r? Okay, well, r, it starts there at that point. That point is on that curve which has that equation as given, it's the inner radius, right? And thus I get that lower bound. For the upper bound is defined by that point which is on that curve which has that equation, again, as given in the statement of the question, and therefore my upper bound is 2. Right? And so, hey, no sweat, nothing to it. This is a perfectly well-defined integral. Oh, by the way, notice I wrote down r dr d theta all as a single thing, thus guaranteeing that I wouldn't forget my stretching factor. Right? And it's easy to convert the integrand here. This integrand is just 1 over r. And we've got a super duper easy integral. Nothing to it. No improper anything. No square roots. Right? Just good old, plain old easy integrals. After all, the integrand is 1. Life is good. Okay. Okie dokie. How we doing? Ready, happy? All right. Here's a harder one. This one's downright weird. Let's look at a spiral. This is the spiral defined by the equation r equals theta. And let me draw what this spiral looks like. There's my spiral, r equals theta. Okay, and so what I'm going to do is I'm going to ask to compute an integral, and again, let's not worry about why, what the application is, what's the integrand, whatever. But I want to take this region here, and it's tempting to say, oh, okay, well that's like almost like a triangle, but not quite. It's also got this little divot taken out of the corner in here, and that's annoying. That's just the way the spiral is put together. Okay, now there's a temptation to look at the curve, to focus on the curve, and think, oh, well, on this curve, drawing out the curve, I start off with r equals 0, which puts me there, and then as I move around the curve, just think about your movement. I've gone all the way up to 5 pi over 2, and so doesn't theta go from 0 to 5 pi over 2? And that's a mistake. We're not going around the curve. We're not slicing up the curve, right? We're slicing up the region itself. So the region itself, which I just erased, right? That region, I could slice that up. You got options, I suppose, but I like to think of it as from 0 pi over 2. That's me slicing up that region. 0 to pi over 2. We'll worry about the r's later. Don't worry about the r's right now. Everybody good? See that this is 0 to pi over 2? Yep.
What about the little spot that you said wasn't included?
Oh, yeah, we'll get to that. Yeah. No, that's coming. Yeah. Okay, so now with the theta bounds identified, 0 to pi over 2, let me draw this theta slice. Let's think about the r bounds. What about this? Here's my first value of r. So you can. So here's the answer to your question. In recognition of the fact that this curve starts off as taking out that little divot, right? My r does not start at 0. My r starts on that curve at some point, and that curve is this curve, which has that equation, and therefore here's my starting value of r. And where it gets a little confusing, second time, figuring out the ending value. Let's see, color choices. I'll use red. That makes sense. Green to start, red to end. There's that ending value. Now here's what a lot of students do wrong. A lot of students say, okay, well that point's on this curve, and this curve has this equation. And so a lot of students will write down, oh, okay, well then R2 must also be theta. Not so. Okay, you got to keep in mind that we have already made the constraint that theta is between 0 and pi over 2. Theta is between 0 and pi over 2. R equals theta is this little bit of curve right there. Right? So the point that I'm looking for the values of theta that I'm interested in this slicing process, that's the curve, R equals theta. I'm looking at what I'm going to think of now as being a different curve. I mean, it's connected, it's part of the same curve, but the difference is that for those values of theta, this is now what you get when you go an additional 2 pi around. You do an additional full turn. So for these values of theta, the equation is 2 pi plus theta. Or if you prefer, you could say, look, I've gone an additional 2 pi around, and so R is 2 pi bigger, if you just want to think of it a little bit more loosely. Okay, so there's those bounds, and that gives us this integral. Theta goes from 0 to pi over 2. Right? R goes from theta to theta plus 2 pi. And there you go. And don't forget your stretching factor. Again, we spent so much time focused on the bounds. This would have been a great opportunity to forget that stretching factor, right? But if you always write down RD theta all at the same time, you got a little insurance policy against forgetting that stretching factor. Okay. Okie dokie. More examples. Okay. Well, let's strategize for a second here. So when should you use polar coordinates? We've got this new tool in our toolbox. When should I use it versus when should I use another similar tool? Right? Rectangular iterated integrals are a perfectly serviceable tool. Then I've got this other tool. They do kind of the same thing. When should I do which? There is no hard and fast rules on that. A certain amount, some extent, the answer to the question is gain familiarity with your tools. Right? The more familiarity you have working with your tools, the more you'll be able to make good decisions about when to use what. That said, some sort of general guidance is as follows. Be on the lookout for circles. I mean, the point is that circles are hard to write in in rectangular coordinates. Square roots, if you're in rectangular coordinates, those square roots get into your bounds. We just don't like that. So it tends to be the case that your domain is easier to describe if there's circles involved. And there may be other situations where your domain might be easier to describe in polar coordinates. So that's one thing to sort of ask yourself. And if there are circles in play, that's a strong hint that maybe, not necessarily, but maybe polar coordinates are the move. On the other hand, I mean, while the domain is usually the biggest problem, right? Sometimes your integrand actually might look better in polar coordinates. I mean, these instances they happen sometimes, right? But be on the lookout for x squared plus y squared. That simplifies nicely in polar coordinates. It becomes r squared. Right? We sort of saw an example of that here. Here in rectangular coordinates, that simplified actually quite nicely to just 1 over r. So you can be on the lookout for that as well. But no hard and fast rules, and sometimes it might actually be good advice to just try it both ways and think about how it would play out in either case, and then do whichever one seems easier. Okay, back to examples. Let's suppose we are interested in this sort of partial eclipse shape here. Okay, now I think about rectangular slicing. It's pretty easy to persuade yourself that that's going to be a bummer in one of two different ways. You either have these 3 regions here, or if you slice the other way, then you have these 3 regions here. Either way, you've got 3 regions. That's annoying. We don't want to do that. Let's call that Plan B. Yes.
For domains like these, will we just be given an equation and then expected to draw?
No promises. The question will be doable by techniques that I've given you in the class, and I don't constrain myself on test questions. Yeah. So maybe not. It depends on the specifics. So here, all we're given is I did sort of implicitly give you the equation of that circle, right? But I didn't give you the equation of this circle. I just said the unit disk, and so it's on you to decide. Yeah. Okay. Circles, right? We got circles all over the place. Let's think about polar coordinates. And here we go. Let's think about the range of values of theta. By the way, common mistake that students make is to think about their theta slices like this. That's absolutely inappropriate nonsense. That doesn't make any sense. That's not how theta is defined, right? Students tend to think in terms of, theta is defined as an angle from, the middle, the center, and then interpret a little too liberally the center of whatever makes my life more convenient, right? So, not so. Theta is always measured off the origin, right? So this is what theta slices look like, right? And it's weirder, arguably, maybe, perhaps, right? But that's the way it is. So be careful with that. Don't misinterpret what theta is. That being said, here's our starting value of theta, and there's our ending value of theta. Now, there's a nice trick you can pull to find what these theta bounds are. One thing you could do is you could analytically you could solve for where is this point that's the intersection of these two circles. You can write down the equation of both circles, and you can do algebra, and that's fine. And likewise here. But the slick way to do it is to recognize that being as it is a radius of this circle is 1. Likewise, that being a radius of the same circle is also 1. And this being as it is a radius of that circle is 1. And so altogether, I've got myself equilateral triangle. And I already know the angles in an equilateral triangle, and specifically then to the point, I know what that angle is. That angle is pi over 3. So it's a slick move. You'd be surprised how often this comes up, though. So heads up. Be on the lookout for that. Nice tricks. Tool for your toolbox. Analogous argument down here. That's an equilateral triangle, and thus negative pi over 3. Bounds then. For a given value of theta, there is a theta slice. And, I'm going to be starting at that point. That point is on that curve. That curve, you could write the rectangular equation of it, I suppose, but knowing that it is the unit circle, boundary of the unit disk, right? That's the unit circle. It's a lot easier just to write it down immediately in polar coordinates. That's what we need anyway, is R bounds. And so your R bound, lower bound is 1. Right? Your upper bound comes from that point. That point is on this circle. This circle has this equation, and make that an equal sign because it's the boundary. And now you've got a little task ahead of you to figure out how to rewrite this equation in polar coordinates. And so let me just say ... there. So we've talked about how to do that, right? You just plug in the conversion formulas between polar and rectangular, and you can simplify as appropriate, and you can convert that given rectangular equation into this needed polar equation. Exercise for y'all. Make sure you can do that. That's going to come up a lot, right? And we've already done them, but make sure you can remember how to do those. All right. Of course, now the last step is solve for the variable that you need. We're looking for R bounds at this point, and since we're looking for R bounds, we solve for R. Good news, it was already solved for, and there it is. Okie dokie. I want to show you one more example of this. Now, this is a historical example. This is actually this is really interesting how this came up. So this specific integral, is actually a really, really important integral. And very briefly, just for context, I want to tell you why this is an important integral. Some of you all have taken Calc 2 course here at Duke. If you did, you probably saw a little bit of discussion of probability. And side note, probabilities are very often computed with probability density functions, specifically integrals of probability density functions. And as it turns out, this function is the formula for a extremely common probability density function. Not just coincidentally common, but a really fundamentally natural probability density function called the normal distribution. We compute probabilities from integrals of such PDFs. So integrals of this function are really important. And of course, now y'all know, those of you who've had some probability, recall that the way you do this thing called normalizing a PDF is to compute the total integral of it, namely from 0 to infinity, and then scale so that that integral is equal to 1. So we need to be able to compute this integral. This is a big deal in probability. Okay. Bad news. The antiderivative of this function can't write it down in what we call closed form. The only way to do this is to write it out as a power series and integrate the power series. So if you want to write down an antiderivative of e to the negative x squared, like in terms of, like exponentials and polynomials and, I don't know, do logs come up or something? But I want to write this down as a formula without summations. You can't do it. Can't be done. It's not that we don't know how to do it. It's that it can't be done. Right? So there's a really important integral to compute, and I can't find its antiderivative. Therefore, I can't use the fundamental theorem of calculus, which is our favorite way to compute integrals. Right? So we've got a nasty problem here. Important integral can't do it. So a couple of hundred years ago, somebody figured out the clever way to do this, and this is super clever. Very, very clever. So it's a great example, partly because we're going to end up using polar coordinates. That's weird, but it's also just of historic importance. This is a calculation that is historically curious. So here goes. This integral, I'm going to call it J, just to get the name. We're going to start off by computing J squared for reasons that'll become clear eventually. So here's a representation of J squared. Now notice that's J. And this, now it doesn't immediately look like J, but in fact it really is. It's the same formula as the formula we wrote up there for J, right? It's just that I use a different dummy variable. I'm using Y instead of X. Whatever, it's a dummy variable. I can call it Q. Whatever, it's the same calculation, it's the same Riemann sum type, so it doesn't matter what you call it. So there's J squared. Now, first slick move I'm going to do is I'm going to take this integral, recognize that, look, it's a number. It's called J, right? It's some value, and being as it is a number, I'm going to stick it inside of the Y integral. It's just a constant, perfectly legal. Okay, now, next slick move. I claim that we can take this e to the negative y squared, and this is going to seem crazy, but then I'm going to put it inside of this integral, and it seems like I'm kind of, can you do that? Can I take that function of y and put it inside of the x integral, like so? And the answer is, yeah, sure, no problem, because, look at this, it's a function of y only. It's a function of the outside variable. So for the purposes of the inside integral, it is to be treated as a constant. It is a constant. Whatever value of y is, as I'm computing that integral on the inside, we treat y as a constant. So this is just another example of, you can move constants in and out of integrals, no problem. So having done that, let me recognize that I've got an integral in the xy plane where x and y both go from negative infinity to infinity. That means I'm doing a double integral of r over all of R2, the entire xy plane. And I can rewrite my integrand by just properties of exponentials. That's just algebra. No big deal. Okay, so we have successfully turned a question that we don't know the answer to into a seemingly harder question that we don't know the answer to. Right? Now, Sometimes in math, this is a weird fact, but this is, I think, culturally significant. Sometimes the way you solve a math problem is to turn it into a harder problem. Or at least a problem that looks like a harder problem. Not because harder is like better or something, right? But because when you turn it into a harder problem, among other things, you've also turned it into a different problem in a different context in which we have different tools in our toolbox, right? So sometimes just, look, if you don't know where to go anywhere, right? If you're trying to get down, sometimes, look, I can't get down, there's nowhere to go. Well, then go up. Maybe there'll be a way to move around horizontally up higher, and then you have a passageway to get down or something. So that's what we've got here. So we have turned this into a harder problem, and in this context of double integrals, I have a different tool, and that is to do this integral in polar coordinates. Now, here it is. Theta goes from 0 to 2 pi, r goes from 0 to infinity. That's still all of R2. It's just I'm slicing up R2 in polar coordinates instead of rectangular coordinates. So I haven't really done anything. Don't forget your stretching factor, of course, right? And rewrite your integrand, of course. And thing of beauty, now this inside integral is perfectly doable. This is an easy Calc 1 substitution rule, right? You let u equal to negative r squared. Your du is going to look other than a constant, just like that. So easy substitution. It's all downhill from here. Now you've got to write it as an improper integral, with limits and, blah, blah, blah. But I mean, it works out fine and dandy. I would even say easily in polar coordinates. So anyway, it's beautiful. Keep in mind, by the way, what we just computed there was the square of the thing I'm actually interested in. So that means that the original integral is square root of pi. So anyway, it's a lovely calculation. And like I say, important and historically curious. So I just feel like when you're doing polar coordinates, you have to do that example. Okay, so enough polar coordinates. We're going to take this same idea. Let me go back over here. The big idea on integrals and polar coordinates was you can view formulas as a change of variables function. Compute your stretching factor once. Make sure to memorize what that is. And then observe that in doing the pullback, everything that you need to see over here, you can see just as well without pulling it back. It's all about understanding, well, what do various kinds of slices look like? Right? Those slices look like that, and these slices look like that. So just understand what your slices look like. Don't forget your stretching factor, and you can do integrals in any coordinate system you like. And that's what we're going to do next. We're going to do cylindrical coordinates. So I've got various formulas to convert from cylindrical coordinates to rectangular coordinates in 3 space. They're a few pages back in the notes. You can just choose to interpret that. Oh, I'm going to view then that I've got x, y, and z as functions of r, theta, and z, and that is a change of variables function in R3. And I can, there's some work to be done here, but you can compute all those partial derivatives and arrange as a matrix, Jacobian. May take the determinant, et cetera, and nice punchline. Not terribly surprising, but anyway, nice punchline is that just like with polar coordinates, your stretching factor is just r. And I say not terribly surprising. After all, don't forget, cylindrical coordinates we like to think of as it's polar coordinates in R3. It really is polar coordinates pretty much. And so, of course, not surprising that we end up with the same formula we had in polar coordinates. Okay, so the only thing that remains is to understand what slices look like, and this is just a matter of thinking through some equations. A theta slice, keep in mind what that means. It means I'm looking at the theta axis. That means I'm fixing a value of theta. Every point on this theta slice in our theta z world, every point on that theta slice just represents, a single fixed value of theta. What does that look like in cylindrical coordinates in XYZ space? Well, that's what you get if you fix a value of theta. That's how you measure theta, right? It's this angle measured off of the XZ plane, positive X portion of the XZ plane. So that's what a theta slice looks like. A little bit weirder, what does an R slice look like? An R slice, well, we're fixing a single value of R. What does the equation R equals constant look like in XYZ world? Well, okay, if R is a constant, then we get this kind of, I mean, it's part of a cylinder. Right, like this. So, a little weird. It's a slice that's not flat. So, weird, but nevertheless, that's what it looks like. And then what does a Z slice look like? Well, there's really no surprise there. Z is, after all, still Z, so the Z slices look like Z slices, and that's easy. Okay, so off you go. Right? Don't forget your stretching factor. Figure out the bounds on your domain by doing the appropriate kind of slicing. Phooey on the pullback, you don't need that. Everything you need is over here. Let's do some examples. So here we go. Let's look at this upper semi-ball of radius A. So this top half of a ball. Right? Start slicing it up. Now, I'm going to make an arbitrary choice, no particular reason. I'll come back and talk about this in a few minutes, but let's do our slicing in that order. dz on the inside, dr second, d theta on the outside. By the way, let me observe. Notice I've already written down simultaneously my stretching factor because I'm scared to death that I will forget it. Right? And if I didn't have this little safety measure, I'm sure that I would eventually forget it at some point, right? So this, don't trust yourself. Why? Why would you trust yourself, right? To remember something when you can have a system that will help prevent it. With the decision made that we're going to do theta slicing first, we've already talked about what theta slices look like. Theta slices look like this. Now, the geometry in these questions is unavoidable. You just got to think geometrically, think about what your solid looks like, and visualize the geometry of it, right? So this ball, theta slices, I'm going to get theta slices for every value of theta as I go around. And so I'm going to say theta starts at 0 and goes all the way around and then ends at 2 pi. That's just what the slices do, right? I mean, each individual slice for a given value of theta looks something like that, all the way around. Okay, next. For that theta slice, we ask the next question. The next question is R. What's the range of values for R? Okay, what do R slices look like? And I emphasize, not R slices of the whole thing, but R slices of the theta slice, right? We're looking at R slices of the theta slice. So imagine like a little cylinder up here. That's what an R slice kind of really looks like. But how does that cylinder, that R slice, intersect with our existing theta slice? Well, a little segment like that. And again, you got to see the picture. You got to think about it geometrically. We're going to start there at r equals 0, and we end here. Well, we've got a little geometry problem now. Where is this point where I end? Well, you've got to think about the geometry and think about the equations that I'm given. This is, here it is. This is a ball of radius A, and that point is a distance A away from the z-axis. So r is A. And you can write that down in equations if you prefer. But so 0 to A. Okay, so attention now focused on the R slice of the theta slice, and want to know the range of values of Z. Okay, well, Z starts there in the XY plane where z is clearly 0. Z ends there. Picture tells me that that's on the surface of the sphere. The sphere has this equation, right? So we've got a point. The point's on a surface. The surface has an equation, and now we have to solve for the relevant variable. Again, a lot of students mess this up. A lot of students will put like r squared plus z squared as the upper bound. That doesn't make any sense. We're looking for a bound on the values of z. You've got to solve for z, right? And so solve for z in this equation. You get that. That's your upper bound. So our z bounds are that. So, morally the same process as with regular rectangular triple integrals. You know, slice up, keep track of what your slices look like. Think about slices of slices. Bounds come from points, which come from surfaces, which come from equations. Right? It's that same game, just different coordinate system. And don't forget your stretching factor. Let's see here, the other order. An other order. Let's say we do our dz on the outside, dr d theta on the inside. Things change a little bit, right? Your z slices are going to go from 0, right, up to, well, here's what z slices tend to look like, but that last z slice is going to be up there at the top where you can easily see z is a. Here's a generic z slice. Theta goes all the way around. Right? You got to see it from the picture. Thank you, picture. Make sure you have a good, decent picture. Make sure you can draw decent pictures. Again, I remind you, it's a very important skill. It's not just going to, you've got to practice and make sure that you learn the tricks. So please watch those videos if you're not already pretty decent at drawing these pictures. Theta goes from 0 to 2 pi. Right? Now, we focus our attention on a theta slice of our z slice. Something like that. And not hard to persuade yourself that r starts at 0. You can see it right there in the picture. It starts on the at the center of that slice on the z-axis, however you want to say it, and then it ends at a point that's over here on that edge. Don't forget that edge is on this sphere. That sphere has the same equation that we mentioned in the previous. This time, of course, though, we're looking for r bounds, so we're going to solve for r in that same algebra, and thus we get those r bounds. So the geometry is different, right? The slicing is different. It looks different. It's a different kind of a picture, but the structure of the argument is really the same thing, just different details. Okay, last comment, and I guess we'll have to call it a day. Your strategic choice. Which way should you slice in cylindrical coordinates? There's 6 choices. They're all legal. Right? And of those 6 legal choices, there's really only 2 that make any sense. Vast majority of cases, again, I could probably come up with some obscure, if I really wanted to, dream up some unnatural oddball case. But, so often that it's really not worth considering other cases. You're going to want to keep r and theta together with r on the inside. And then dz is either on the outside of it or on the inside of it. That's really your 2 choices. Nothing else really makes much sense. So pick from between these. Notice those are the 2 that we just did examples of. And those are your choices. And again, a huge point, dx, dy, dz. Volume form, right? Your dv. Write it down all at once and as a tool for helping you to avoid inadvertently forgetting. You'd be surprised how common this happens, inadvertently forgetting your stretching factor. which is r. So always write down, when you're writing down your differentials, when you're deciding which order to go in with your slicing, write down either r dr d theta dz or r dz dr d theta all at once, all at the same time, so you don't forget. Okay. Good stopping point for today. See y'all later. Have a good Wednesday.